All right, hi folks. This video is just to get you refreshed on the exponent rules. And there may be a need, or rather no need for you to go through this video, but just in case, here are the 6 exponent rules that we need to have down for this unit. So everything is timestamped below, so you can jump around to wherever you need, but I'll go through all 6 of them. And starting with the product rule, we should be able to build up to all of our other exponent rules. So let's go ahead and get into it. You may have seen this exponent rule before. If not, we can start it over from scratch and just think about what happens if we have a to the m times a to the n. For the purposes of this demonstration, let's just say that m is equal to 3 and n is equal to 5. In this case, a to the m would be a to the third. A to the n would be a to the fifth. And if you have an exponential like this, a to the third would be 3 a's multiplied together, right? A cubed, 3 a's multiplied together. A to the fifth, likewise, would be 5 a's multiplied together. Right, and so in total, we have 8 a's, right, being multiplied together, or a to the 8th. Right, so that's how we're getting this product of a to the m times a to the n equaling a to the m plus n, right? 3 plus 5, a to the 8th. Right, and that'll work for any numbers for m or n. Right, we can use this for something similar over here. So if we have a to the m over a to the n, this time let's say m is equal to 9 and n is equal to 7. Right, so a to the 9th would be 9 a's multiplied together. And a to the 7th would be 7 a's multiplied together. Right, with 9 of those a's multiplied up top, 7 multiplied down below, we can start reducing things. So for each a that I reduce out of the numerator, I'll also reduce one out of the denominator. And that leaves behind 2 a's in the numerator, a squared. Right, and you'll notice 9 minus 7 is equal to 2, and that fits our exponent rule here. Right, that a to the m over a to the n is equal to a to the m minus n. And this also will work for any numbers m and n. We can apply something similar for our power rule. I'll cover up the right-hand part of the rule. Let's start with the left. So a to the m to the n, let's say m is equal to 4, n is equal to, what have we not used yet? Let's say 6. Right, so a to the 4th to the 6th, or you could say a times a times a times a to the 6th. Right, so just expanding out your a to the 4th. If we take this product to the 6th power, then we're really going to multiply that product by itself 6 times. So how many a's are we actually multiplying together? Well, this is a 4 by 6 array. So that tells me that there are 24 a's in total, a to the 24th. Right, and 4 times 6 is 24, and that's how we arrive at this rule of a to the m times n. right? How might we use that for an exponent of 0? I think you already know this rule, just to really show where that comes from. Let's rewrite that a to the 0 using a different exponent. Let's say m minus m, right? Certainly m minus m is equal to 0, so this should work out just fine. If we take a look at our quotient rule, right, then any subtraction in our exponent can allow us to rewrite the exponential as a fraction. So set up our fraction, we'll have the same base, a to the m, and I'll start color coding this, so that'll be our green m's. Make this one blue. I'll zoom out for a sec, but all we're using here is quotient rule. So once you set it up like this, we're using quotient rule and then rewriting to fit the left-hand part of the quotient rule. So a to the m over a to the m. Okay, but if you just reduce, then that just reduces out to 1. So that's where our 0 exponent rule comes from. A to the 0 is equal to 1, and that is true for any positive base a. Here comes our next one. What about the reciprocal rule? Let's cover this up and just look at the left-hand side. So a to the negative m. I'm going to do something similar to what we did for the last one and just rewrite the exponent with a 0. So we have a to the 0 minus m, right? 0 minus m certainly is equal to negative m. So rewriting that should be fine. We can do the same thing with our quotient. So a to the 0, and that'll be over a to the m. So just using quotient rule. And if we rewrite the numerator, because we just saw that anything to the 0 is equal to 1, and this would simplify out to 1 over a to the m. Right, and that matches our rule from above. Right, there's also an alternative rule to the reciprocal, or rather an alternative version of the reciprocal rule. So what if we didn't have a to the m, but what if we had 1 over a to the negative m? Right, well, in this case, we can do some similar business, right? Let's keep this fraction. I'm just going to duplicate that. And then instead of 1, I could put a to the 0, right? We've already established that anything to the 0 is equal to 1. In this instance, I have another version of quotient rule, right? But this time we're taking out the fraction and just making a single base. So that would be a to the exponent from the numerator minus the exponent from the denominator. So it's 0 minus negative m, right? 0 minus negative m. Or that would be a to the 0 plus m, or that would just be a to the m. Right? So it is equivalent for us to say that 1 over a to the negative m is also equal to a to the m. Right, so these are the 5 exponent rules that I think you are most likely to have seen before today. You also probably might have seen the rational exponent rule, but we'll dive right into that. I was going to say in a moment, but it's not in a moment, it's now. We're going to dive into it now. Here we go. Rational exponent rule. All right, so what is a to the 1 over m? All right, what is a to the 1 over m? To do this, I'm actually going to just use like a normal number, not a variable. Just to do a little demonstration, and hopefully that'll make it clear. Let's say, 3. Let's just say 3. Hopefully this is not too much to say that that is equivalent to 3 to the first, right? And if we then ignore the 3 and just look at the 3 to the first, I could then break that exponent of 1 up into 1/2 plus another 1/2, right? 1/2 plus 1/2 is certainly equal to 1. These 2 expressions are equivalent. Right? And if we use our product rule, the addition of exponents symbolizes a product of exponentials, right? So by adding these bases, we can just split this up. So keeping the base of 3, this 1/2 comes over here, this 1/2 comes over there, and we're multiplying in the middle. Right? So these two expressions are equivalent to each other. Well, now I have one thing, and I'm multiplying that thing by itself, right? These are the same factors being multiplied together. And what do we have, in our prior knowledge that describes that? That would just be a square, right? So really what we're doing is we have 3 to the 1/2, we're multiplying it by itself. So that's just the square. Right, so these two expressions are equivalent to each other. Right, and this should also make sense because I could just distribute the two, or not distribute, but multiply the 2 in with the 1/2. That would become 3 to the 1st, and that's equal to 3, right? So the first step is equal to the last step. Really, all 5 of these expressions are equal to each other. Right, but in those 5 expressions being equal to each other, I could just take any 2 of them and use those expressions to make an equation. Right, if this first step is equal to this 5th step, I could just write that as a statement, right? That 3 is equal to 3 to the 1/2 to the 2nd. And once I have that, let's ignore all the green bits and just focus on this equation. Right, if 3 is equal to 3 to the 1/2 to the 2nd, and I want to really know what the value of this expression is with the rational exponent, rational meaning fraction, right? And with a fraction in the exponent, then it would probably work for us to square root. Right? The square root and the square will take care of each other. And just leave behind a 3 to the 1/2. The square root of 3 does not reduce. Right? And that is the equation that tells us the significance of this 3 to the 1/2, right? The 1/2 in your exponent is indicating a square root. Let's do that again. Let's use different numbers, right? So let me clear this out. Let's say we're going to start with 5, right? And we saw that that was equivalent to 5 to the 1st. And similar to the 1/2, I'm going to go for a different fraction now. I could make that exponent of 1 just be rewritten as 1/3 plus 1/3 plus 1/3, right? 1 is certainly equal to the sum. So these two expressions are equivalent. Right, again, we could use our product rule. So 5 to the 1/3 times 5 to the 1/3 times 5 to the 1/3, right, which is really one factor, 5 to the 1/3, is being multiplied by itself over 3 iterations, which is a long-winded way of saying something's being cubed. And in this case, it's the 5 to the 1/3 that is being cubed. Right, which again should make sense because if we multiplied this 3 in with our 1/3 according to the power rule, we would have 5 to the 1st, which we had earlier up the line, and it's certainly equal to 5. Right, so if all of those lines individually are equivalent to everything else in the chain, right, I can say that 5 is equal to 5 to the 1/3 to the 3rd. Right, we want to find out the value of the thing inside the parentheses. Let's cube root this time. Right, so the cube root and the cube take care of each other. 5 to the 1/3 then has to equal the cube root of 5. Right, I hope you're picking up the pattern that's going on here, right? We could do this again. We could do it with 4ths and 5ths and all this and that, right? But really, if you have a base to a fraction, specifically 1 over some number, right? That number is informing you of the index of the root on that base, right? So if I have a to the 1 over m, that is equal to the mth root of a. Right? You may also see this written, I mean, it's equivalent, but you may also see this written as a to the 1 over n, equal to the nth root of a. There's also a version of this rule that combines the rational exponents with the power rule and says that a to the m over n is equal to the nth root of a to the m. Right, all three of these being different versions of the rational exponent rule. All right, so there we go. That is page 1, just refreshing you on your exponent rules. Yeah, you can go ahead and close out the video and then get back to the notes.